Hello, my name is Alexander Goldstone and I am a master's student at George Mason University. My presentation is on the analysis of various passivation species on germanene, armchair, and zigzag nanoribbon physical structure and band structure. Germanene is the 2D germanium analog of graphene, and like graphene, it has a 2D hexagonal structure and is a semi-metal with its bands touching at the K-point. Unlike graphene, it is a buckled structure with 0.7 angstroms buckling, similar to the other group 4 graphene analogs silicene and steinine. We started this research by looking at the effective width on the bandgap of hydrogen passivated armchair germany nanoribbons. As you can see, the nanoribbon has the same hexagonal shape and the buckling, but the hydrogen atom places itself between the two germanium atoms. This material likes to transition between semiconductor and semi-metal depending on the width. As you can see in this bandgap versus width chart here, it starts with 0.738 eV bandgap at the 3 atom width, increases slightly, and then becomes a semi-metal at the 5, 8, and 11 atom widths. The overall bandgap decreases logarithmically as the width increases. As you can see, the 3, 4, and 6 atom band structure charts reveal a semiconductor, while the 5 atom width chart shows a semi-metal with a very linear EK relationship. In this study, we looked at numerous passivation species using the quantum-wise ATK software, all using the DFT calculation method and the GGA-PBE exchange correlation. Most species resulted in a honeycomb structure regardless of width, however, there were a few exceptions. Nitrogen and oxygen resulted in unique structures, whereas fluorine, chlorine, bromine, and iodine were non-symmetric. By non-symmetric, I mean the 6 bonds that make up the hexagon are not the same length. Of note, fluorine became more symmetric as width increased, while the other structures became less symmetric as width increased. Here we see the various geometric configurations the passivating atoms can take. In the case of hydrogen and fluorine, the atoms remain unbonded, where in the case of carbon, phosphorus, and the rest, the passivating atoms bond to each other. These additional atoms on the bottom right are simply a result of the molecular viewing software used and do not affect the band structure results. We see from the transport direction that on cases here like carbon, phosphorus, and hydrogen as shown earlier, the passivating atoms place themselves between the germanium atoms, where here as in the case of sulfur and selenium, the passivating atoms are in plane with the germanium atoms and their bonds cross over. Of note, only in the 5-atom case for fluorine and selenium we have this interesting inversion of bonds occurring in the transport direction. This configuration can be more clearly seen from this vantage point. All other configurations for all other passivating species simply resulted in the typical buckling zigzag structure and a crisscross structure from the other vantage point. For the non-symmetric species of chlorine, bromine, and iodine, it can be most clearly seen from iodine in the transport direction that this honeycomb lacks symmetry. While chlorine looks alright, as we increase the width, it becomes increasingly non-symmetric as the other structures. However, they all bear a similarity in the band structure, where the conduction band is nicely curved, while the valence band in comparison remains relatively flat. And as an example of what I mean by unique structure, this is the result for the nitrogen geometry optimization, and oxygen bore a similar result, clearly not a honeycomb structure, nor 2D. This graph shows all the different passivating species bandgap versus width for the different nanoribbons. I know it's a bit much, so I have some notations here to help us out. Here we see hydrogen and fluorine, which bear a similar bandgap versus width relationship. Both of them become a semi-metal at the 5-atom width point. Meanwhile, phosphorus, arsenic, sulfur, and selenium all have bandgaps in a similar range over width compared to the others. Carbon, this orange line, remains an outlier in its behavior, as does tellurium for the 2 points we were able to calculate. In the case of chlorine, bromine, and iodine for the 3-atom case, they all result in a bandgap around 0.5 to 0.54 eV. In the case of the zigzag nanoribbons, although they retain the same hexagonal and buckling configuration as the armchair ones, they are all semi-metals regardless of width. Here we see the 4, 6, and 8 atom with hydrogen passivated zigzag nanoribbons, and you can see here that the bands do indeed touch at various points. However, instead of being a simple curve, we have these discontinuities known as kinks. In the zigzag nanoribbon case, different species converged than in the armchair case. For example, chlorine created a stable honeycomb configuration as seen here, whereas carbon did not. There are only two geometric groupings for the zigzag nanoribbons: the alternating structure, where the germanium atoms either overlap or are beside each other, and the symmetric structure, where the germanium atoms are beside each other but they zigzag across. However, this results in three groupings for the band structures. We have, in the case of hydrogen as shown earlier and sulfur as shown here, two kinks around either the zeta or gamma points. In the case of phosphorus, arsenic, and selenium, we have a valence band that pierces well above the Fermi level to touch the conduction band. And in the case of fluorine and chlorine, we have a single minimum, nicely curved, not a kink, at the zeta point. In conclusion, the results of the study show that germanene is indeed a 2D honeycomb buckled semi-metal material like graphene, and that armchair and zigzag nanoribbon configurations can be created for all passivating species except nitrogen and oxygen. The armchair nanoribbons alternate between semiconductor and semimetals with a cycle of 3 atom width band gaps. The armchair nanoribbon passivating species also show patterns among multiple geometric groups. The zigzag nanoribbons, on the other hand, are all semimetals regardless of width. They come in only 2 geometric groups, yet show 3 different unique band structures. For my future research, I would like to examine up to 11 atom width structures for each passivating species to confirm the cyclical bandgap pattern I did in hydrogen. I would like to use machine learning to analyze the geometry and bandgap data and see if we can find accurate groupings for the behaviors of these different passivated nanoribbons. I would also like to perform spin-orbit coupling analysis as well as measure the magnetic moment to see if any of these are useful for spintronic devices, and also do more research into the zigzag nanoribbon passivation, potentially an opening of the band gap and further analysis.